Good afternoon. Thanks for being here. I think the previous speaker left with the mic, so I guess I'm going to make use of this one, but that's fine, yeah. So, should I use this device? Okay. Does it work? Green. Green. Backwards. None of the buttons seems to work. Ich brauche Hilfe. Oh, this one, sorry. It's too big to be seen. Okay, great. So thank you for being here. So I'm going to talk about data protection in the framework of what has been discussed so far. And as we all know, there's an ongoing disaster related to data protection, right? This is one attempt by the US authorities. They have set up a website that probably most of you know, the official, let's say, wall of shame, at which all the breaches related to medical data have to be essentially mentioned and in some way exposed to the public. And it turns out that there are in the order of 5 declared breaches per week, each affecting more than 500 patients. But in some cases, it can be 1,000, tens of thousands, hundreds of thousands. In other cases, even millions of people who are affected. And the hope is that by this transparency, the organizations are going to make a better job in terms of data protection. Unfortunately, as we know, this let's say, public shaming and the legal deterrence doesn't seem to really work. And this is just one example among many other of a major breach that happened a few months ago and that affected millions of people. So I think there is a major challenge here. We are witnessing a kind of slow disaster that is going on and that has to be addressed in some way. The good news is that there exist a number of technologies for privacy and technology protection, most of which are vastly underused in the framework of medical data for historic reasons, for inertia, for a number of reasons. So there's traditional encryption that aims at protecting data at rest and in transit. There is homomorphic encryption. I'm going to say a few more words about this one that is less known. There's secure multi-party computation that I'm going to detail as well. And then there are trusted execution environments. So if you believe a given vendor, then you can buy a processor that will provide you with appropriate, let's say, so-called enclaves in which you can do protected computations. But unfortunately, this cannot be mathematically proven, and you have to trust the vendor to use this. So we are not, let's say, pursuing this kind of solution for the moment. There's differential privacy that is probably known to some of you, and then the famous blockchains. Well, so that's essentially the landscape or the set of devices that are available. And so the question is how to best make use of those, right? So, and in particular, when we do multi-site studies, right, because you're talking about data at scale, machine learning, so data reside at different places. So what are the options? Essentially two main options. The first is to keep the data at each of the sites, which is useful, especially if you don't want to go for a cloud solution, and there is a better control of the data. Or upload the data in the cloud and take advantage, essentially, of the well-known, let's say, strength of cloud computing, right? So, first case, assume the cloud is fully trusted. You assume that, I don't know, for example, the cloud service that is provided by Amazon or by Microsoft or by Google is fully trusted. In this case, you could even store the data in clear text. This never happens in practice, but is essentially something that can be an option, right? In practice, when you talk with cloud service providers, they will tell you, no. Let's be cautious here. We're going to encrypt with keys, cryptographic keys, but we, let's say a cloud service provider, are going to control the keys, right? And by default, what you get in terms of offer from these companies, right? Now, in this case, data sharing is easy, right? And the computation in the cloud is easy as well, right? Now, the second case is, well, what if you don't trust the cloud? You say, no, that's too risky. And this is usually the behavior here in this country. So for example, this is the one I mentioned previously, the case one, cloud fully trusted. This is typically the solution that our US friends would use. They say, we put the data in the cloud. That's it, right? And problem solved. Here, or in the case of Nordic countries, say Denmark or Estonia, they would put this in a governmental cloud. Right? Here in Switzerland, but it's also the case in Germany, we tend to be even more cautious and say, no, that's not good. We have to keep the data under our own control. And so one option in that case is that to encrypt with keys we control ourselves. Right? So, but then it means that if you as a user upload the data, they are encrypted with keys that belong to you, which means that the cloud cannot make computations on them. Right? And you lose most of the benefits of cloud computing, because then it's just a big repository somewhere. Right? And if you have to make computations, you have to download the data, decrypt the data, make the computation, re-encrypt the data, and upload the data, right? Which is cumbersome. Right? So then another solution is to make use of something that is called homomorphic encryption, something that has been known in computer science for decades, but that is still relatively exotic in the framework of bioinformatics. But now is the time to look at this option in more detail. So assume, this is just a toy example, that the researcher at the bottom of this picture is willing to upload two values, the encryption of 3 and the encryption of 5. This is what she does. So she doesn't upload 3 and 5. She uploads the encryption of 3 and the encryption of 5. And this appears as just an omelette of bits, right? That are of no meaning to the cloud service provider, because the cloud service provider does not have the keys. Right? But the beauty of the thing is that then the user can say, please make computations on those data. So compute me the encryption of the sum of the data that are under encryption at your premises on the cloud, right? On the cloud. So it will ask to compute the encryption of 3 plus 5. So it doesn't know, the cloud does not know it is a 3 and it is a 5. It just has the encryption of 3 and the encryption of 5. And out of this, it will compute the encryption of 8. Right? It's a very elegant trick. It's on Wikipedia, it's on textbooks, it's everywhere. So it's not something that we have invented. It is mathematically proven. And now it's time to use this tool, because this is exactly a response to the kind of concerns that are faced by this community. So this is a nutshell how homomorphic encryption works. So you can go either, so you take two operands A and B, you can compute an operation on A and B and then encrypt, or you can go downwards from the two operands A and B, you encrypt A, encrypt B, and then you compute a combination of the two encryptions, and on the bottom right, the two values are essentially the same. Right? That's what it is in a nutshell. So this enables computations directly on encrypted data. The second fundamental, let's say, technique to be used in this framework is secure multi-party computation. Right? So assume there are sites that do not fully trust each other. Say University Hospital of Basel and a hospital in Boston and one in Beijing. Right? So they're willing to work with each other, but they're under different jurisdictions, so they cannot fully trust each other. So then what would they do? They would use secure multi-party computation. So what this technique does is that assume that there are here 5 stakeholders. This can be 5 people, or it can be 5 hospitals or 5 pharma companies, who each of them has an input. The input can be a scalar, can be a vector, can be a matrix, whatever. It can be a file. And they want to make a computation. So each of them provides an input. For example, it's a piece of a cohort, right? And they want a result to be computed without any of them seeing the inputs of the other ones, right? So this is called a multi-party cryptographic protocol. And so here it works. Here you see so it would take, let's say, 3-4 hours of mathematical. So I just repeat. You want to see the animation again? Please enjoy it. Voila, boom, voila. So abracadabra. So, but it's mathematically proven. It's again, it's textbook stuff, and the outcome is that each of the parties is going to obtain its own share of the result, or the common result, if this is what is agreed, right? So the results, the output y1, y2, y3, etc., which are computed as a function of the different inputs, right? And now by combining homomorphic encryption and secure multi-party computation, it is possible to set up, let's say, systems that provide, let's say, an appropriate level of performance. This is what we explored in this project, in the framework of the SPHN, Swiss Personal Health Network, and brings together an ethicist, a specialist of machine learning, a geneticist, a specialist of blockchain and distributed systems, and myself, so a kind of multidisciplinary team to come up with appropriate solutions, in particular to address the main privacy, security, scalability, and ethical challenging of data sharing for enabling effective P4 medicine, but also to deploy an appropriate set of computing tools. So we have to show that it works. For this, we have to bring the software into the hospitals, and this is where the fun really begins, right? So, okay, this is a website of the project. So, for example, the idea is then once this works at the level of this nation, right, Switzerland, to be able to ask how many patients have BRCA1 and breast cancer, or what is the survival rate for cancer patients undergoing a given chemotherapy, right? So the data exists to respond to these questions, but the problem is the data is locked. So with such system, it will be possible to unlock the data and to have statistical significance for these responses, and then to move at an international scale. So for this, we've developed a tool set called MEDCO, again here the website, that provides the collective protection on medical data, right? So, and it makes use of some of the techniques that I've mentioned, so homomorphic encryption, secure multi-party computation, differential privacy, which I guess you know what it is, and a blockchain. So the idea is to be able to generate a query, so a researcher to generate a query to a confederation of sites or hospitals, for example, and obtain, say, in the first stage, just the number of patients that correspond to specific criteria, and then to be able to make computations on this data while keeping the data at the different sites, right? So, okay, this is how it works. We make use of I2B2, which is probably known to some of you, which is, I mean, it's nothing special. It's just a way to explore cohort. And the secret source, or it's not secret because it's public domain, but what we do is we make use of a tool called the Unlinks that provides this privacy-preserving computing framework, right? And so for this, we worked with 3 hospitals, with the CHUV in Lausanne, with the HUG in Geneva, and Inselspital in Bern. We're also talking with the university in hospital in Basel, with the ones in Zurich. We're also talking with the Germans. We also talk with the people in Boston. But let's say for the moment, we focus on those 3, just to start somewhere. So to deploy, let's say, the software in each of those places, right? And to validate this with end users. So here is where we stand. So this is, we start in April 2019 for this specific project, and the end of the deployment is going to be in September 2020. In the coming weeks, we're already run a test with, let's say, synthetic data to show that everything works smoothly. Now, so I'm in computer science, and so we ran, of course, a number of software packages at EPFL. That's easy. Now, bringing software to the hospitals is a different feeling, right? Because then they say, here are the 35, let's say, requirements that you have to fulfill. You have to be OWASP compliant, blah, 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 blah. So this is what we're currently working on. So I've recruited a team of no less than 4 let's say, software developers working on this part of the thing. And so we are now relatively close to target. So the first use case will be the Swiss molecular tumor board, and the ability, in order to bring the ability to make the queries that I mentioned previously, and then for a given patient that is under evaluation, to be able to compare with similar patients, where similar, of course, needs to be appropriately defined, and then compared with this, with what oncologists like to work with, which means overall survival. Whereas on the x-axis you have the time, and on the y-axis is essentially the number of patients who are still alive after a certain time, right? So this is typically the kind of feature that we want to provide in this framework, right? So in the foreseen user experiment, what we will do is to provide a first stage with a cohort selection, and then step 2, typically a survival analysis. This is for the case of oncology, but it can be used for any other case. I know people in this room are more interested in infectious diseases. It can be, of course, be transposed for these kind of diseases as well. Right? So first use case is melanoma. So we take the characteristics of various variables and then make, let's say, computations on those. Here is a small demo on how this works. Let's see if the demo itself works. Yes. So here we put ourselves in the shoes of a researcher, and we assume the researcher to have access to 3 hospitals in which the data are going to be kept where they are with homomorphic encryption and secure multi-party computation. So the researcher here selects a given pathology. So which pathology? Well, in this case, it's a melanoma, and then wants to find all the patients for which that correspond to this disease. And so without moving the data from those 3 hospitals, the data remain there. We already have the response here. There are actually 633 subjects. And then we want to refine the request. We want to see, but not only, now out of this subset, we want to know those who have, let's say, an annotation value BRAF. We take all the zygosities. We take an annotation value that is V600E, right? So we refine, let's say, the investigation. And once we run this again with these additional criteria in order to find how many correspond to this. And again, we do this without moving, so data remain encrypted at the premises of the different hospitals. So here the computation takes place. Let's say it's real-time. Let's say evaluation of the unfolding of the thing, and then we have the outcome where you see for each of the clinical sites how many correspond to the criteria that we have set. Right? So once we have this, so then one concern, of course, with this kind of tools is what the performance can be. The good news is that with the set of optimizations we have brought, the overhead is actually highly acceptable. So here we have really stress test the whole system. We have pushed it to, we have done experiments with 28 billion, not a million, 28 billion data points. And as you can see, the response time is in the order of a few tens or hundreds of seconds. But the overhead brought by, but this is what the database would take anyhow. So the overhead brought by the let's say, security is minimal. And these few hundreds of seconds have to be compared with how much it would take to lawyers of the, or DPOs of the hospitals to agree on that thing. And then we are not talking about hundreds of seconds, of course, right? It's a different scale. Okay, so now, once we know the kind of, let's say, cohort that is available, then the time starts to make an analysis and to go towards machine learning, right? And so for this purpose, to make statistics, right? So what we can already do under the protection that I've mentioned are the functions that are mentioned here. Including, let's say, linear regression, logistic regression, and we're currently working towards, let's say, small to medium level complexity neural networks. Right, so this is how this would work. So here's the researcher, here are the three, let's say, institutions that are involved. And so the query first defines the query, so training a linear regression model on specific attributes, and then each of the data providers is going to locally compute on data that remain encrypted a given function on its local database, and each data provider encrypts the results, and then the results get aggregated and provided to the query, and the query can then decrypt and decrypt and compute the final result she is entitled to obtain. Right, so just to make things a bit more concrete, let me provide you here with a toy example. So here there is, let's consider linear or logistic regression. So we want to compute the line, let's say, that fits these 6 dots best, right? And so if all the data are available in clear text locally, that's trivial, right? You just compute this and you to this line, and to do this, a gradient descent can be the solution. But that's a trivial thing. If you want to do things on data that are not available, right? If it is distributed, then there is a risk that, for example, if the data, the 6 dots, are actually in possession of 3 different entities. So the first 2 dots with the first entity, the second 2 dots with the second entity, and the 2 last dots with the third one, then you got something of this kind, right? Then this person will have the first 2 dots and believe that the truth is this one. The second will believe that actually it's this one, and the third one will have this perception, right? So each of them essentially gets it completely wrong, right? So what needs to be done is to emulate the collective computation by doing something that is shown here. So to first the encrypted summaries, and then to collectively aggregate the summaries under encryption, and then the aggregated summary encryption is switched to the querier's keys, and then the queriers receive things which in such a way that collectively they find the correct minimum. Right? And so again, here we have made let's say simulations and made measurements, and we see that the runtime is again in the order of tens or hundreds of seconds, and we have also checked the accuracy that we obtain with existing benchmarks to evaluate how much we lose in terms of that accuracy, and I would say the results are very promising. So the main features in terms of functionalities. So what we provide here is an opportunity to do a count and select of patients based on Boolean combination of inclusion and exclusion of genetic and clinical criteria on the data that is distributed at different locations. This for the exploration, and then for the analysis is to compute, what we can do is to compute basic statistics and set operations, and we perform distributed basic machine learning tasks, right? Voilà. So, and then on the security privacy side, what we provide is end-to-end data protection, which means at rest, in transit, and during the computation against unauthorized data access. No single point of failure. Only the investigator can obtain the query and result. And there is a minimal risk of re-identification from aggregate data released by means of differential privacy. Voilà. Yes. Either plan B if this device, voilà. Ah, blockchain, voilà. That's maybe the reason why, right? So blockchain. So the role of the blockchain. So as you know, blockchain is currently the most hyped topic in computer science. Blockchains can be helpful, nevertheless, in this case, because the blockchain are actually an immutable log that make it possible to store the access to the data, right? And this emulates what happens in a single hospital. If you want to do this in a collection of hospitals or institutions, and none of them is willing to be the cop for everyone, then you can decentralize the trust by making use of a blockchain. But this is not a Bitcoin-like blockchain, right? It's a blockchain that is going to be a closed or permission blockchain, which means that it's way, way simpler and less energy, let's say, hungry than the existing, let's say, cryptocurrency blockchains. Right? So we are also working on this topic as well. So let me conclude, Schlussfolgerung. So it is possible to securely make computations on decentralized data without moving them. So that's a very important fact that is very well known in computer science, that I think is a response to many of the concerns of this community. Right? And so what we have done is that we have developed a unique know-how and provably secure open source software solution to provide what? To provide privacy-conscious medical data sharing. Right? So, as we have seen, also we have managed to reach a reasonable overhead, right? At least for low to medium complexity operations, which are actually the ones that are the most frequent in practice, right? And so we are currently deploying these solutions at 3 Swiss hospitals. So the ones I've mentioned, Bern, Geneva, and Lausanne. But as mentioned, we're also talking with the 2 other ones, right? The most Nordic ones, so Zurich and Basel in Switzerland, and then beyond, right? So, and as mentioned, the first applications are going to be in oncology, but we would be happy also to talk and to consider, let's say, application of this to infectious diseases, and I provide also here a few links in case you want to explore this a bit more. Thank you for your attention.